Hello, welcome to ISC 22. My name is Matt Demas, CTO at GigaIO. I'm here today to talk to you about NEC vector engines running on GigaIO's rack scale compute platform. So the agenda for today is we're going to talk first about what is GigaIO and what is its memory fabric. Then we're going to talk about composing devices or composing access to devices across GigaIO's memory fabric. Next, we'll get into scaling out across the rack scale compute platform, and then finally talk about the performance charts that you'll see when we add NEC vector engines to the GigaIO rack scale computing platform. So GigaIO's purpose was to bring cloud flexibility to your on-prem data center. Traditional servers, when you're looking at AI and HPC, have one major disadvantage over the cloud, and that is when I buy a server, everything that lives inside that server is now confined to that server. So if I want to go access resources outside of the server, I have to then go across antiquated networking technologies that then have to add latency and reduce bandwidth over something where if I could plug all those devices into the same server, I could be significantly more flexible and have a significantly higher performance. So in the cloud, when I run these types of workloads, I'm able to go dynamically define and say, I want to have 5 GPUs or 10 GPUs or 20 GPUs. Yes, there are limits, but I'm able to just with a click of a button determine exactly what size system I need, and the cloud gives it to me. And that can be a huge advantage when you're trying to write codes, write software, because you can really let your software define what your hardware is going to require. And then the advantage of the cloud is I'm able to go make my hardware meet the requirements of that software. Traditional on-prem environments, that's not possible, right? Because at the end of the day, I have sheet metal, and that sheet metal lays into a motherboard. And then that motherboard has a specific number of slots that things can plug into. It can only cool a certain amount within that system, and that defines what a workload can do on a single system. So the goal of GigaIO, again, is to break those constructs and really drive into what we call rack scale computing. So we do that using GigaIO's FabreX rack scale computing platform. Some of the key advantages, we work on all workloads, right? So whether you're doing data center workloads or databases or AI, HPC, DevOps, it doesn't matter, right? Our platform works at the BIOS level, and it allows us to go deliver this dynamic computing environment regardless of what workload is going to run on top. We interoperate with hybrid clouds or multi-cloud environments. So if you want to have the ability to still burst to cloud, you can still do that. And then the benefit is we give you the same flexibility the cloud gives you when you're on-prem, so you're able to go maximize your hardware on-premise before you have to go burst up to the cloud. We truly do bring that software-defined hardware concept to your on-prem resources. We also give the ability to create impossible servers. So the cloud today has limits, right? Those limits are whatever can physically fit inside one of their big systems or be composed and sometimes to their systems, because they do actually use composition sometimes. With GigaIO, those limits really go away. It becomes what the software can do now, not necessarily what the hardware can handle. So we've done things like compose 32 GPUs to a single server before, because we can break outside the confines of sheet metal and of a motherboard and really drive to what the software needs it can utilize. We really help optimize resources because we actually break the bounds of a server, but that means if I can stop putting things inside of a server or allow other servers to directly access resources living inside your server, that means if a workload's only using 2 GPUs and the server has 8, I'm no longer isolating 6 GPUs. I'm using those other 6 for some other job. I'm able to see them as a pool of resources and able to go let the software pick exactly which hardware it needs to go run most effectively. Then we also maximize the device compatibility. So today, some of the biggest challenges you're running into with your systems are, I bought a set of servers 3 years ago. There's a new accelerator out, but that accelerator isn't certified for my server, right? So I have to buy a new stack of gear to go be able to use these new accelerators to do this new cool stuff, right? And so by composing those devices in, and even disaggregating some of those devices, we'll talk about here in a minute, you're able to really allow those devices to be connected into servers without having to live inside. So some of the server compatibility list restrictions go away because we've added this rack scale infrastructure. And then, of course, because I can redefine my hardware, I can lay it out differently, I can let my software be optimized and make my hardware wrap around it, I can really help decrease time to insights. So those are some of the key advantages you're going to find as we go through this, but now I'll dive into what GigaIO's FabreX rack scale computing is really all about. So GigaIO is a memory fabric underneath. And what a memory fabric means is I'm not talking necessarily across TCP or InfiniBand as my primary communication path. Every device within a server, within a rack of servers, has memory inside. Whether I'm talking to a NIC or a GPU or a storage device, whether I'm talking to a server, it all communicates memory to memory at one level or another. A GPU connects to the memory bus bar of a server. So when I'm talking GPU to GPU within a server, they're all going through their memory bus bars down to each other and communicating GPU to GPU. They're able to bypass CPUs and do a lot of really cool stuff there. But at the end of the day, everything living within the server is able to go talk memory to each other. When I go beyond that, in traditional data center, I can't do that anymore. I have to then go out another transport mechanism and translate to another protocol, and then go across the networking switch, hit another server, translate back, and then ultimately try to get back to memory again. So with GigaIO's memory fabric, we're able to go communicate directly as memory. And by doing this, it can really help significantly increase efficiency. Also, give deep insights into what else is within the fabric, within that rack. So everything that our memory fabric touches can now be directly accessed via memory. So if I have GPUs living inside these resource chassis on the right-hand side, or whether they're living inside the server here on the left, I can talk directly to any of those devices. If I want to talk directly to the memory of that server there, I can do that. Right? What GigaIO's memory fabric allows is it allows node to node, node to device, or device to device communication directly as a direct memory access anywhere within that fabric. So no more RDMA, we actually operate in true DMA fashion. Not only can we operate and just communicate as memory, but we can also add other protocols across that memory fabric. Things like NV over Fabric, if I want to deliver VLANs, or GPU Direct RDMA, if I want to use some of the more advanced GPU-enabled functions when I'm doing a multi-node deployment. We can use libfabric and MPI, TCP to allow applications that are set up to run and operate with a specific protocol. We can still allow them to run, and they'll run at a lower latency because I'm not having to go translate into other cards. I'm just simply making my memory communications ride a different protocol. So we can still make those things perform better than they normally would and allow application compatibility even though you're running across a new fabric type in the GigaIO memory fabric. So how does this physically work? Right? The memory fabric does ride a PCIe switching infrastructure. And why this is important is every device that you're running inside of a server is natively running PCIe. Right? They're all plugging into a slot in one way or the other. Even if I'm running the new SXM platform of GPUs, those are still plugging in PCIe into the motherboard. That is the native interface for every device into a server. So by riding a PCIe fabric, we're ultimately able to go keep things at their base language. So there's no translation. There's nothing else that has to happen. It's simply allow these devices to communicate to any other device across this fabric. So riding PCIe, we enable something called non-transparent bridging. And what that means is I'm able to go create links between memory devices anywhere throughout this fabric and allow them to talk directly to each other. So non-transparent bridging is generally used within a server today for most Linux environments, and this allows things like peer-to-peer between GPUs that are riding on the same server, things like that. But now we've taken that technology and broken it well beyond the confines of the sheet metal and delivered to the full rack scale. And that's why you see rack scale computing. So here within this PCIe switch, you're going to see standard servers. These can be servers with devices living inside of them. They can be pretty bare level systems if you want to. And they can be AMD, Intel, ARM, doesn't really matter to GigaIO. Then you add other resources to the fabric. Things like accelerator pooling appliances. These are just chassis that are purpose-built to hold devices, whether those are NICs, vector engines, GPUs, DPUs, it doesn't matter. From there, you can add other things like GPU servers. These are servers with other resources converged inside. And then it drives into storage. We have storage pooling appliances that are generally called JBOFs, right? Where I may want to have NVMe devices that I deliver out to the servers. I can also have storage servers, which are servers full of NVMe that I can make VLANs and use NVMe over a protocol. And then last is our memory pooling appliance, which is a big pool of memory that can be either shared by servers, be composed to servers to allow both DRAM and PMEM to increase the computing capacity of any server or set of servers. So we talked a lot about the memory fabric and the ability to go intercommunicate to any device or any server within that fabric. Now we also have the concept of what we call simple composition, right? And with simple composition, instead of having things converge in servers, it's actually utilizing the boxes we just kind of showed you here. So you're going to look at a traditional rack here where I have GPUs and storage and memory all living within servers. Let me go ahead and disaggregate that now. I'm going to go take those devices out and put them into resource chassis like the ones we just mentioned. Right from there, I can go ahead and take these devices. These devices consist of storage, memory, GPUs, accelerators, DPUs, vector engines, anything you may have. Send that to the Fabrics Fabric Manager, and we're able to then go create new bare metal servers. And these are all done within a matter of seconds. So I send an API and I get a brand new server. Here you're seeing a 3 GPU server and then a storage-centric server. And then the last one is even 4 servers that are all composed. And then that memory fabric still allows us devices to communicate freely between those servers. So really kind of break the bounds of what a traditional server looks like. It's now I have resources in a rack, and my application picks and chooses what resource it needs to most effectively do its job. Some of the key advantages here is, again, creating impossible servers, where I can do things like 32 RTX 6000s with a single node, right? I can create servers with petabytes of storage inside. So many different options I can do when I'm not confined by the motherboard and sheet metal, right? I can deploy these in seconds, so I can reconfigure my cluster to go meet a new scientific need. I can maximize resource utilization by making sure that I have the right types of resources within. I'm only replacing that resource when it really needs it. Do I need to replace my servers now, or do I just need to replace GPUs? Do I need to upgrade my network, or can I keep the existing network while upgrading my servers? So many different options you have when you've disaggregated those components, and you can really, replace them as needed, but also make sure you're only delivering exactly what's needed, and so you have all the remainder of your resources left for another job. And then, of course, lastly is heterogeneous compute, right? You have this concept of, I've got lots of different workloads over here running throughout my environment, but if I buy servers that all look the same, I have to make those workloads change to fit that server. If I can be heterogeneous, take advantage of any of the new 204 accelerators out there that are in stealth mode now, or take advantage of cool things like vector engines that can really assist in traditionally CPU-related jobs. It really allows me to go open up my data scientist's eyes and my AI scientist's eyes and say, hey, do what you want, build what you want, and we'll make your hardware work for you. Right? And so it truly unleashes that heterogeneous compute environment. So you may have heard the word composability in the past, because companies like HP and Dell, they've been throwing that word out there for a while. And when they've done that, they've all really focused on storage. Storage requires, doesn't have very strong latency demands. It's pretty easy to compose. It does deliver the memory to a remote server, and that works well, right? But then you drive into all the rest of the stack. And that's where Fabrics really excels, because we've really focused on that PCIe layer. With the PCIe layer, I'm able to go do nanosecond speed latencies, right? I can deliver significantly higher bandwidth. I do bidirectional bandwidth compared to unidirectional, right? And then here in the near future, we're going to be embracing CXL. So we've been a founding member of the CXL consortium because we've understood that memory is key to the next generation of compute. And so as I look at the full rack as one layer of compute, and look at the memory as the fabric that kind of binds them all together, CXL is going to be so important in the future of that as we get to true cache coherency. So some of the major advantages, be able to manage CapEx and OpEx appropriately, depending on what you need to upgrade, what you need to change, getting to impossible servers, and then again, scaling resources as you need to, but all that really drives towards a faster time to insight, right? When I'm able to go give the exact right hardware for that software, I can get my insights significantly faster. Now, we talked about hardware a lot, and hardware is important here, but without the right software, none of it makes any sense. So GigaIO has been really built around an open ecosystem. So that's why we open source all of our drivers, so that our libfabric driver and our TCP driver and every other fabric driver, all those things are open source so the community can kind of see what's going on. They can add to it. They can build on it. Right? If you look at this memory fabric, you see the power of it. Well, the community is going to be out there to go really help drive this and build this into the next level of HPC and AI. Right? Everything's based around Redfish APIs. And so we did that again. It's an open standard around out-of-band management platform connectivity. So since we're moving devices around, intercommunicating between devices, it's like an out-of-band management function. So we embraced that Redfish, and everything's built around the Redfish API. We also worked with a lot of different vendors to make sure that it was seamlessly integrated in fact, one of our key decision makings in the early on was to not have a GUI. We wanted to make sure that everything done in our platform was done through your third-party management tools. We want to be invisible to you and your environment. So to go on that, right, we also offer the ability to integrate into your existing environment or even do all the way up to full pre-integrated solutions. Whatever makes the most sense, we can deliver. If you want to add a switch and GPUs to your environment, or if you want a full rack delivered with GPU chassis, servers, storage, and networking, GigaIO is here to go assist in whatever you need. Here's a list of our northbound integration partners. We're very excited about our newest one, Bright Computing, now part of NVIDIA. With Bright, you're able to go manage your hardware at the Bright level with both a GUI as well as CLI, and then have that integrate with some of the most popular workload managers. Now I'm going to kind of break down a couple of our key rack scale implementations. So first we're going to start with our GigaCell. This GigaCell is kind of our entry point. It's your 4 servers, your GPU chassis, storage chassis, and a switch. Those all intercommunicate via memory. They also all compose. So anything you put into any of those resource boxes can be composed to any server, and I can go intercommunicate with memory between all of them. That drives me into my GigaPod. This is your single rack. Everything within here is composable, can compose together, also has memory access, but it goes to the true rack scale level. And that drives into the Giga cluster, which is many of these pods. So here, each rack is still composable. I can deliver devices directly to any server, but then I can also reach out to any device within any of the server within this entire cluster. So the memory fabric reaches out much wider, and it will go reach into any GPU, any memory space, any storage device that I want to, and go pull directly from it, even though I didn't compose it to my physical server. And then we can bring that down to the tactical edge with our GigaCell Extreme. This allows us to go to the remote edge, go to archaeology sites, or go do remote imaging, or work on next to our soldiers. Right? Whatever we need, we can go deliver compute and compute level AI out of the far edge using data center class systems. Here's kind of some of our key use cases, right? From analytics to HPC, visualization. I think those are all pretty self-explanatory. We've been seeing a lot with the modeling and digital twinning, VDI all the way down to brownfield installations. Some of the use cases that we've had kind of the most success with, where customers really understood the value and have really kind of latched on. The first one is universities. So with universities, I have lots of different schools that all have different hardware requirements. They all get their own grant money. They all do their own thing, but they need a stack that can be dynamic enough to take care of each individual school's problems, and do that in a very in a way that truly meets the performance requirement while at the same time meets flexibility. And that's what GigaIO's CONDO cluster approach will do for them. Next, we have our high frequency trading. So we talked about having nanosecond latency and having ultra high bandwidth bidirectional. Well, it's also the concept of not having to read or write data. I can simply read directly from the memory of another server. So when I have systems doing trades, I can read directly from that memory space, and it allows me to get significantly lower latency, which in the high frequency trading space means more money. Next, we're going to talk about some of our customers. One of our customers is TAC at UT Austin. We're a part of their Lone Star 6 cluster, where they want to be able to go compose NEC vector engines, FPGAs, and other GPUs, and really give their customers a dynamic hardware experience. And then, of course, we have our San Diego Supercomputer Centers. We're part of the NRP platform, which is I want to have a global or a countrywide multi-site deployment where when the customer connects in, wherever their data is closest to, they can process that data. Their hardware will change and adapt to go meet the requirements of the codes. And it's really the next level of what HPC has to offer. All right, now we're going to talk about the NEC Vector Engine and some of the performance work and testing that we did with GigaIO FabreX. So part of the testing foundation was we wanted to go look at vector engines converge within a box, whether it's in one box, two boxes, or whether it's composed in. We wanted to see the difference in performance. So we talked a lot about how composing in these devices can get a lot of flexibility. But if that impacts performance in a negative way, then that doesn't make any sense, right? I'm not going to spend so much money on these accelerators. They can do so much amazing things just to go lower the power of them. So if I want that flexibility, I still want to maintain the performance. And so that's what's really important when we did this testing is making sure that as we composed, we didn't lose the performance of a converged device. So the vector engines are really good at AVX codes, at traditional CPU-related workloads. That's really where they excel. And they can do things significantly faster than traditional code can on a CPU. So you're able to take a lot of the traditional codes out there that were CPU-only codes, just simply recompile them and then go deploy them on these vector engines and get 10, 20, 100x faster time to insights. So it can be a very powerful tool. And then you look at the ability of composing multiple of these together or spreading a job across multiple servers with them inside. Then you take that advantage and you multiply it at significant orders of magnitude. So here's the test that we ran. So first on the left, you're going to see the converge tests, right? This is going to be a single node, multi-node test. And we're going to have them either plugged in, all at the same server, or have two different servers. And then you're going to see the right side, we see them composed. So on the left side, I have two GPUs on one side of our accelerator pooling appliance composed with a single server, or a single switch composed with a single server. And then on the right side, you see one vector engine plugged into each side of our chassis, of our accelerator pooling appliance, connected to our switch, and then each connected to its own unique compute node. So I'm going to run a job that either runs two vector engines on one node, or I have two nodes that each have their own, and I'm going to distribute that job across both nodes. So the tests that we run are going to be HPL, HPCG, stream, SVD, and decision tree classifiers. So here's the performance output from all the testing that was done. Right inside here, you're going to see the far left, that's your converge test. That's the vector engines living inside of that server and then running directly. And then you're going to see the second one where everything is composed to a single node, and then the third one is composed to two separate nodes with one vector engine in each. So as you notice here, the converge versus composed are nearly identical. So key point to note here is I've added the flexibility of being able to compose 1, 2, 4, 8 number of, or 16 vector engines into a single box, but I haven't lost the performance in doing so. And that was critical to show as we worked with NEC and some of our customers together, is that I can add flexibility without losing the performance. And you can see some here, like in the stream use case, where when I can compose to multiple servers, why would that be faster, you may ask, right? If I had multiple servers converged, multiple servers composed, well, the difference is being I have a memory fabric interconnecting them. So I'm no longer going through another protocol like Ethernet and InfiniBand. I'm actually gaining performance in this very small use case because I'm able to go ahead and utilize that memory fabric and the low latency between them. So you're saying that at most I'm on par, sometimes a little bit better. No matter what, adding the flexibility of GigaIO's memory fabric and our rack scale computing platform really is only an advantage. The performance is maintained or even increased, while at the same time I gain a whole lot of flexibility. So in summary, right, when IT is being asked to do so much more with the same IT budget, how do we go solve that, right? Let's become more flexible. Let's increase utilization. Especially as these lumpy workloads are coming out there where I may need a lot of this one day and I may need significantly less the next day. Let me go put myself in a scenario where I can deliver exactly what's needed and not have to have resources kind of isolated or in solitary within a server because I only need so much where I don't have the right quantities of that type of resource, right? Then a rack scale computing platform really embraces a lot of the kind of newer initiatives within computing, which is kind of embracing the whole heterogeneous compute at the same time, embracing sustainability, right? Making sure that we're being smart with the money, smart with our resources, and making sure that we're being smart with the planet. FabreX Memory Fabric really kind of embraces the power of the NEC vector engine because the vector engine is really there to go work with a lot of the CPU-enabled codes. So you're going to have your GPUs, you're also going to have the vector engines to really help empower the CPU side of those codes to get better. So I have GPUs for AI workloads, vector engines for different types of codes that are going to be more CPU-centric. But running all of this across the GigaIO memory fabric allows you to really get the best of both worlds. And then, of course, lastly is by having the flexibility to go add more or add less when needed can really help improve the performance of the vector engine overall because I can meet that workload, that amount of data with the right number, the right kind of devices at the right time. And of course, we're both available in production today. So thank you again for your time. My name again is Matt Demas, CTO here at GigaIO, and my email address is below. Thanks.